So today I'll be teaching you for Fulkerson algorithm. Let me try to explain to you what the problem is. We are given a graph g is equals to v comma e, which is a set of vertices and the set of edges. And in this graph we are given a source S and we are given a destination T. You can think of these as the source of water and the destination where we want to send the water. And each of these edges, you can think of them as pipes. Now you want to send the water from source S to destination T, and you want to send the maximum amount of water. So this is the problem of max flow, which we are going to discuss today. Now before we move on, let me try to explain to you certain terms that are required for Fulkerson algorithm. So the first term is the capacity of edge, which we will consider in the following video, and we'll denote it as C of sub E, and we will also denote a flow along an edge. We'll denote it as F of E. Now note that the flow value F of E can have a maximum value equal to CE. So FE will always be less than equal to CE. Now let me tell you what the steps of this algorithm are. So first you initialize the value of flow on every edge, and you initialize it with the value of 0. Once you initialize it, you create a residual graph G of F. Then you find an augmented path in the residual graph, and then you update the flows in the original graph. I'll try to explain to you what this residual graph and the augmented path in the residual graph is, and then we'll go over this algorithm once again. But before we do, let me also tell you an important property of this graph, which is the conservation. That is, the amount of flow of water entering a vertex should always be equal to the amount of water or flow leaving the vertex, which is the conservation property. Okay, it is quite obvious, right? Now, one more question I want to ask you is, if I add a constant amount of flow to every edge on one path from S to T, on every edge, if I add a constant amount of flow, is the conservation maintained? Yes. It is quite obvious, right? Because any edge that is incident on a vertex is increased by b, and any edge that is leaving the vertex is incremented by a value b. So the incoming flow is increased by a constant amount b, and the exiting flow is increased by a constant amount b. So the conservation is maintained. Now let me tell you what is a residual graph. The residual graph is created by taking the same set of vertices in the original graph and a different set of edges. I'll tell you what those edges are in a minute. So for every edge E in the original graph, what do? We create two edges even in E2. So for every edge in the original graph, we have two edges even, which is the capacity of CE minus FE, and it has the same direction as the original edge in the graph. And we also create a backward edge having the capacity of F of E. Now let me try to explain to you by these diagrams what do I mean by even in E2. Let's say I have an edge from a vertex U to a vertex V in the original graph. Now this has the capacity of 10, and this has the value of flow along it of 4. Now in my residual graph, I want to create an edge which has the amount of flow that I can send from U to V. Now if the flow is already 4 and the capacity is 10, so I can send 6 more along this edge. So that is my residual capacity, and I represent here by a forward edge, and the capacity for this edge should be 6. This is exactly the same thing, CE minus F of E. This is the residual capacity, that is the residual amount of flow that I can send along the edge from U to V. And also I have a backward edge from the vertex V to the vertex U, and it has the value of 4, which is the amount of flow. Now I'll try to explain to you the reason behind why are we creating a backward edge from V to U. Well, our motive is to find the capacity or find the flow that we can send from U to V. Let's say that if you are supposed to find out flow in a graph and you don't know this algorithm, how would you proceed? You would proceed by notion of backtracking, that you send a certain amount of flow along a path and you realize, okay, maybe I should not have gone along this path, I should have taken a different path. At every vertex we are thinking whether we should go in a certain direction. So if we want to backtrack from a certain amount of flow that we have already designated, we want to be able to return back and find out. So the notion of backward edge only states that if you have sent a flow along a path U to V, you should also be able to send the same amount of flow back so that you can consider other paths. Now I'll tell you how is it useful once I define you what the augmented path is. So I define my augmented path as any path from S to T in the residual graph along which we can send a flow, which means that it has non-zero capacity. So once I create my residual graph by creating two edges for every edge, I have a certain graph with me that I call as a residual graph, and I find any path from S to T in it and I call it as an augmented path. Now how does this help? Let me try to explain to you with an example. Now let's say we have an original graph here, S, U, V, and T, and we want to send the flow from S to T. The capacities are 10, 20, 10, 20, and 30. And the flows originally we have initialized it to be 0. Now if you want to create a residual graph of this graph, we will create two edges for this, one with a forward capacity of 20 minus 0, which is 20, and a backward edge with a capacity of 0. Any edge with a capacity 0 is of no use to us, so we will not create that edge because we can't send any more flow along with it. So our residual graph for this graph is equal to the original graph, GF is equal to G. So is the conservation maintained? Yes, of course, because all the flows are zeros, the conservation is true. Now let me try to find out one path, SUVT. Okay, now how much amount of flow can I send along this path from S to T? Which is the minimum of all the edges in this path, which is 20. So 20 is the amount of flow that I can send from S to U to V to T. So let me send the flow of 20 and I will arrive at this place. I'll arrive at this graph. Now this represents in bracket the amount of flow that I'm sending. Okay, now if I want to create the residual graph for this, so my S to V and U to T will remain as it is because that is the amount of flow I can send, 10 minus 0. There will be no forward edge for S to U and for V to T because the flow is 20 and the capacity is 20 and we can't send any more flow. But there is a backward edge from T to V with a capacity of 20 and from U to S with a capacity of 20. What does it mean? It means it gives us a chance to send the flow back to a certain edge and in retrospect examine whether we could have sent the flow from that vertex in other direction. Okay, so what we are doing in our original algorithm, now I'll explain to you how our algorithm works. So our original algorithm is that first we initialize with flow 0 on every edge, we create the residual graph, then we find an augmented path in the original graph. That's exactly what we're doing. We create a residual graph, we find an augmented path. Augmented path is any path from S to T along which we can send the flow. Once we find the augmented path, we update the flow values in the original graph G, and then we repeat the steps from 2 to 4. Okay? So in this graph, we have arrived at this residual graph, and we want to send the flow from S to T. So we find a path in the residual graph, which is S to V to U to T. Now what is the maximum amount of flow that you can send along this path, which is the minimum of all the edge capacities in this path? which is what? 10. So I can only send 10 amount of flow here. So let me send a 10 amount of flow and update my original graph. So I'm sending 10 amount of flow from S to V, so I'm updating the value to 10 here. One more thing that you need to notice here, that earlier the flow was 20 here, and we are sending a flow of 10 from V to U. Right? So if you're sending a flow of 10 here, it only means that we're reducing the amount of flow that was originally coming from U to V. So we write 20 minus 10 as 10 here. Now also, to maintain the conservation, if we are sending 10 less here, so we should send 10 more here because the flow here is 20, right? So we send the flow of 10 here. Okay, once we have arrived at this graph, we want to create the residual graph. When we create the residual graph, we arrive at this graph. We can see that there's no forward edge for this, so there's a backward edge here, backward edge here. So here we have a forward edge of 20 and a backward edge of 10. So a backward edge of 20 and a backward edge of 10. Okay? Can we find any more path from S to T? No. Which means we have terminated our algorithm. So what is our maximum flow? Our maximum flow is the amount of flows that is 20 plus 10, which is equals to 30. So this is the maximum amount of flow that we are sending. How do we know that it terminates? Well, we can argue that it terminates because whenever we try to find an augmented path, we always find a path with a bottleneck of non-zero capacity. Okay? And we are increasing the flows in every iteration. And since we are increasing the flows in every iteration, there is bound to come a time when we can't increase it anymore because each of the flows is restricted by the edge capacities. Isn't it? Okay, now let's move on to the notion of a cut capacity. What is a cut? A cut I'm defining as partitioning of the vertices of the original graph into two sets, A and B, in which one of them has the node S and the other has the node T. So I can define any cut that is a partition of the set of vertices such that when you take the union of these two sets, you'll arrive at the original set of vertices V, and one of them has S, another has T. Now I define the capacity of the cut as the maximum amount of flow that can go from the set A to the set B. So there are only going to be two types of edges, one that goes from A to B and one that goes from B to A. Okay, so the maximum amount of capacity would be C1 plus C2 and all those edges that have a non-zero capacity and that originate in A and that end in B. So we take the summation of all those and we arrive at a cut capacity. Okay. Now we should also understand what is minimum cut. So we iterate over all the possible cuts and we find out the one with the minimum capacity, minimum cut capacity, and we call it a minimum cut. Let's also examine what would the flow be in this case. So we'll denote f of AB as the flow that goes from A to B. Okay, the amount of flow that goes out of A minus the amount of flow that goes from B to A. So we can say that F out A minus F in A is the amount of flow that is the flow of the cut. Okay. Now let's move on to a theorem called min cut and max flow theorem. Now let me try to explain to you what this theorem says. We have a set A and we have a set B. So we have defined a cut that has a node S and the node T. Now we characterize min cut with one more thing, that when we draw a residual graph of this original graph, Okay, all the vertices that are reachable from S in the residual graph will come in the set A, and all those vertices that are not reachable from S will come in set B, which means that T is not reachable from S and S is reachable from S, so S will lie in our set A and T will lie in our set B. Now why is T not reachable from S? Because when our algorithm terminated, we are not able to find any more augmenting path, and an augmenting path is any path from S to T, and if you're not able to find a path from S to T, which means so T is not reachable from S, so we can put T in the set B. Okay, so I want to argue that the minimum cut capacity is equal to the maximum flow that comes out from our algorithm. Okay, now let's try to examine two types of edges in the original graph that originate from S and that originate from a node in A to a node in B. Okay, now I want to argue that the maximum amount of flow along an edge that originates in A and ends in B is equal to the capacity, because if that is not the case, which means we have a forward edge with a capacity of C1 minus F1 of E. If there is a forward edge, which means we have an edge from A to B in our residual graph, which is not possible because we have argued that all the vertices in the set B are not reachable from S. And I also want to argue that in our original graph, which has an edge that originates in B and ends in A, has the value of flow equal to 0, because if there was a flow, okay, so we would have a backward edge in the residual graph, and if there would have been a backward edge, those two nodes would be reachable from A. Okay, so we can easily understand that these edges have a flow of 0 and these edges have a flow of maximum capacity. And since the maximum flow is equal to the capacity, we can say that the minimum cut capacity is equal to the maximum amount of flow.